This video is part of a course on food physics, of which this is the theory section. The subsection here on conservation and rate laws are the basic ingredients, the basic building blocks for the governing equation for single phase transport. The video before this is an introductory one to this section, and the videos following are on heat transfer, mass transfer, and fluid flow. While the equations are complete here, they are not meant to be a replacement for a course on transport processes. So these are quick introduction to materials that are covered in full-blown courses. We all know these fundamental principles: conservation of energy and conservation of mass. We're going to actually utilize this, write it in an equation form, and to do that, this is our equation form. So in, out, generation, storage, a change in storage. But to do this, we have to first define a system with a boundary, so that these quantities like what's coming in, what's going out, what is generated are more defined. So with those definitions, we can say what's coming in minus what's going out plus what is generated inside the control volume should be equal to the change in storage. As applied to mass, for example, the obvious interpretation of this is like everything has to go somewhere. So this basic principle is one of the two building blocks for the transport equations in single phase. It is one of the two building blocks. It alone is not enough. There's limitations of this conservation laws, the one that we just mentioned. Let's look at a very simple problem. So we have a mass that we know the mass and we know the initial temperature, its specific heat, and then we put this solid in this liquid, and the liquid also we know the mass and its temperature and everything. Okay, so by doing this equation, in minus out plus generation equal to change in storage, we can exactly say what is going to be the final temperature of this system. So it's very powerful, but we will have no clue whatsoever about how long it is going to take to reach that final temperature. And that rate, the time needed, is of course important from a practical standpoint. So that's the limitation of just the conservation law. So we need something like rate law, how fast things are happening. So here comes the rate laws. We need a different rate law for each one of the physics: heat, mass, and fluid, and they are different for the different physics, but the form of it, the construct or the formulas, they are very similar in construct, as we will see. And so let's start from heat conduction. So let's say we have a hot side and a cold side, and heat is conducting along the direction x. Then the heat flux along x in watts per meter square is given by minus k, which is a material property, times the temperature gradient. In other words, heat flux is proportional to the temperature gradient, and the proportionality constant is the thermal conductivity, which is a material property that we often have to measure. And then we move on to mass. Instead of mass transport in a solid, I happen to show that in a gas, where the red molecules are moving into the blue, while they're both moving randomly, just because they're not at absolute zero, and so they have some energy, so they're moving randomly. This in the x direction, the flux is given by this formula. So this mass flux along x in kilograms per meter square per second is proportional to the concentration gradient. So the concentration gradient has this unit, that is kilograms per meter cube per meter, and the proportionality constant is diffusivity. So diffusivity in this case is of the red in the blue, and the unit is meter square per second. So this is the form of the mass diffusion and the rate law for mass diffusion. Likewise, we have for fluid flow. So let's say we have fluid flowing over a solid surface. So on the surface, velocity is 0, and then the velocity increases as you go further from the surface. So the shear stress that a layer feels as it tries to kind of flow over the layer below, it feels a stress, shear stress given in Newton per meter square, that is proportional to the velocity gradient. Higher the velocity gradient, more is the shear stress. Now, before we talked about fluxes, so let's see if this shear stress, we can think in terms of a flux. So the shear stress is in Newton per meter square. So this is equal to, Newton is kilograms times meter per second square, and per meter square. So this I can write kg times meter per second times 1 over second over meter square. So this quantity kg per, so this is momentum. So it's mass, because it's mass times velocity. So it's momentum per unit area per unit time. So it's momentum flux. So this also can be thought of as momentum flux that is proportional to the velocity gradient, and the proportionality constant has to do with the material. So in all three cases, the law that the flux is proportional to some sort of a gradient, the proportionality constant comes from that particular fluid or the particular situation, the temperatures and the material properties and so on. For example, here it's the two molecules. What are their size? What is their temperature? That decides these properties. So in each case, we need these material properties that make it make the law fit the particular material, and these material properties are almost always measured experimentally. So then we have rate laws that say at what rate heat is moving, at what rate mass is moving, and at what rate momentum is moving. And so these now, if I combine with the conservation law, now we can find how long does it take to do certain thing. Now, in a complex material such as foods, when we talk about a material property like thermal conductivity, we can talk about the different mechanisms that it normally represents, like lattice vibrations for solid, molecular movement for gases, and in between for liquids that are closer uh, than gases, uh, but not as close as solids. So we have these detailed mechanisms, but a general comment is for a complex material such as food, it's very hard to figure out all the detailed mechanisms, and therefore what is contributing to what, and come anywhere near predicting some of these properties. So how do we get these properties? We measure them. And prediction equations are available, but these prediction equations are almost all based on measurements. So then these properties, although those equations are written in a very fundamental way, but the way the equations are used is using properties that are from empirical measurements. Likewise for diffusivity. So diffusivity normally represents molecular diffusion, capillary diffusion, then it could have thermally different diffusion, all these different mechanisms. It's really hard to try to say for a complex food material such as food exactly which one is contributing how much or come to any prediction. So again, we do measured values and prediction equations for, let's say, diffusivity. Okay, so this is just to keep things in perspective that although those equations are very fundamental, this is how they are used. So likewise, viscosity represents internal friction forces between adjacent layers, and we can look at detailed descriptions of the molecular processes, but it would be hard to come up with prediction equations for viscosity for most practical food products. So then what we do is we use measured values for most of these fluids. Back to these rate laws, and let's just pick one of them to make a point. So I'll pick the mass equation. It is nice, colorful animation. So it would be easier to make the point with this. Now I want to bring in an important concept of what is total flux. So what we discussed so far are diffusive fluxes, either for heat, mass, or momentum. And to that, we also think of flux due to bulk flow. So let's try to see that using this animation. So here we have the red molecules are diffusing in the blue, and let's think of an imaginary line and let's write the flux expression. So the flux, the mass flux in this case would be the diffusive flux that we just discussed. That's the Fick's law. That simply talks about how many how much of these crossed, like this red one right now, cross this line through simply random movement. The other kind of flux is due to bulk flow, and that's on top of the diffusive flux, like this. So the diffusive flux did not stop, but on top of that we have this convective flux. So in this case, the convective flux is simply the velocity times how much is there. So kilograms per meter cube. That's this one. Okay. And so velocity times how much is there, is going to give us how much stuff crosses this line simply due to this flow. So this concept is universal. The same thing is true for heat or momentum, and it's very important, and I find it very helpful to think of two kinds of fluxes at any given situation. One is due to this kind of random movement, and the other one is due to directed movement, as we saw in the animation. So random one is the diffusive one, and the directed one is the convective flux. Now this is a very busy slide, so let's try to go slowly. What I'm trying to do here is summarize those fluxes that we just discussed, and make sure of the analogies between the three types of transport process. So as I said, it is very useful to think of this diffusive type flux due to mostly random movement, and then convective flux mostly due to directed movement, and then the total flux is made up of diffusive plus convective. Now in the diffusive fluxes, if you look at for heat, its thermal conductivity here, that is watts per meter per degrees Kelvin. For mass diffusion, this is meter square per second. And then for viscosity, it's kilograms per meter second. Now they all look different, and then this quantities, temperature, concentration, they also have very different units. So the analogy may not be as obvious. We can actually make it a lot more analogous, and we can see the analogy very, very easily. All we have to do is, let's say, take the heat one and we divide by rho Cp and multiply by rho Cp. Then the quantity here, K over rho Cp, is alpha or thermal diffusivity, and this has the same unit as the mass diffusivity, which is meter square per second. And the same thing here, viscosity divided by density. So I divide and multiply by density, and then this quantity mu over rho has the same unit as meter square per second. So now all three equations, just slightly rewritten, has the same unit for the proportionality constant, and then the other part is also analogous. So rho CPT is an easy way to think of rho CPT is mCPT divided by volume. So mCPT is, as we know, is joules, is the enthalpy, is the amount of energy content per unit volume. So the unit for rho CPT is joules per meter cube. For mass, the unit is kilograms per meter cube. So you see they're beginning to look very similar. And then rho u is momentum per unit volume, because you can see rho times u is mass times velocity divided by volume. So mass times velocity is momentum per unit volume. So this quantity is momentum per unit volume. Okay, so that's about the diffusive part. Now in the convective part, again things are similar. So as I already said, the convective part is velocity multiplied by how much is there. So this how much is there, rho CPT, as already said, is joules per meter cube. So likewise here, C is kilograms per meter cube, and then here momentum rho u, as I just said, is also in terms of kg meter per second divided by meter cube, momentum per unit volume. Okay, so the convective fluxes, then you can see that they are in exact same format, analogically speaking. So the total flux then is diffusive plus due to flow, diffusive plus due to flow, and diffusive plus due to flow. I find it extremely useful to think of these different fluxes, diffusive, convective, and total, throughout understanding or modeling the physics of a process, uh, because they help me relate to the physical quantities, and they really make it easier to understand, for example, the results from computation and so on. So these are extremely useful concepts irrespective of detailed modeling or detailed mathematics and so on. These are the building blocks for understanding food physics. This video or this module is setting up the building blocks for later deriving the transport equations, the governing equations for heat transfer, mass transfer, and fluid flow. A governing equation consists of conservation equation, like we discussed here, and the rate laws that we discussed. So these details will be done combining them in the later videos, in the follow-up videos, and there will be a separate one for heat transfer, one for mass transfer, and one for fluid flow.